How do enzymes work? Well, one way that we can understand how enzymes work is to use our reaction coordinate. So we're going to review some aspects of reaction coordinates. Truthfully, we've probably gone through the entirety of what I'm going to discuss here, but as we move on in this learning unit to understand how enzymes work truly at the details of the enzyme active site, we want to remind ourselves about how things apply energetically. So we've got a reaction coordinate. Remember, reaction coordinates plot energy as a function of, this is really reaction progress. So going from product or reactants to products here. And again, we see an increase in energy as we go through a transition state, and then we get to products on the other side. So let's highlight some of the pieces that we know. If we look at the differences in energy values, that's going to give us some important thermodynamics parameters. So the difference between reactant and product energies we define as delta G, and we identified this as how much and whether. So that how much piece has to do with the magnitude that we have of the value for delta G. Okay, and we can think of it in terms of this equation, delta G equals minus RT ln of K. And K, right, is an equilibrium constant. It's a ratio of products to reactants. So in this way, the magnitude, the numerical value of delta G is related to the equilibrium constant, which is related to quantities of reactants and products. So that difference in energy between reactants and products is really determining how favorable, I shouldn't use that word favorable, how much product we have with relative to reactant. Okay, so why I didn't want to say how sort of spontaneous we have is because that's really related to what we have here. I'm going to move this over here just real quick. When we think about the sign of delta G, that's really this whether piece. So the sign of delta G has to do with whether it's spontaneous or non-spontaneous. So a negative delta G is a spontaneous reaction. We also could say that we define that as going downhill. However, a positive value for delta G, that is a non-spontaneous process. And we might define that as going uphill. Really, that uphill and downhill refers to whether or not, in this case, the energy of the products is lower than the energy of the reactants. So we can think about it energetically going downhill. And spontaneous reactions happen to do so. Chemistry happens so that things go downhill in energy. That's how we define kind of favorable thermodynamic processes. Okay, so delta G is only one part of the picture of information that we get from our reaction coordinate. The other one is delta G double dagger. And to think about delta G double dagger, we have to make sure that we identify some important pieces on our reaction coordinate. And that is this important piece at the top of our hill, which is our transition state. In this case, the transition state for the uncatalyzed reaction is different than the transition state from the catalyzed reaction. You'll notice, and we probably should have identified this right at the start here, this blue line represents an uncatalyzed reaction, and the red line represents the energetics for a catalyzed reaction. And you'll notice when we were talking about delta G, the blue and the red lines really are the same. And that's going to be an important piece that we'll summarize here in a moment, that energetically there's no difference in the thermodynamics of the how much and whether between a catalyzed and an uncatalyzed reaction. What changes is this delta G double dagger. And delta G double dagger is the difference between a reactant energy and the transition state that's just following it. Truthfully, any delta G double dagger is the energy of an isolatable intermediate or reactant or product and the transition state immediately adjacent to it. So a valley to a hill, if you will. So we have two transition states here because they are different for the catalyzed and the uncatalyzed reaction. So the transition state for the uncatalyzed reaction is higher in energy than the transition state for the catalyzed reaction. Okay, so when we identify the value that we have for a that's not the right height, delta G double dagger here, this is going to be the delta G double dagger for the uncatalyzed reaction. And then this represents the delta G double dagger for the catalyzed reaction. And remember, when we think about delta G double dagger, we are reflecting the how fast. Cannot read my own writing here. The how fast. And there's only a magnitude component to this because delta G double dagger is always going to be a positive value. We're always going up and over a transition state. So that's always going to be a positive energy. But the magnitude of it is going to be related to how fast that reaction is. So this really is a magnitude piece. Okay, and here is where we start getting into some important pieces that we think about here. The magic that happens with enzymes, okay? Enzymes are going to decrease the energy of the transition state, okay? So enzymes make reactions faster by decreasing the transition state energy. Right, so we can see that here. We decrease the transition state energy, and that's reflected in a smaller delta G double dagger, okay? And that means that our reaction is faster. So this is all information that we've sort of talked about already, but where we kind of have some new information here is really understanding how enzymes do this, and importantly, understanding what enzymes can do and what enzymes cannot do. So highlighting here, what we really have is enzymes stabilize the transition state, and they often do so by making interactions. So enzymes are going to be stabilizing the transition state, and they often do that by making interactions. This is a big theme that we've talked about before. When you make interactions, making new intermolecular forces, that's stabilizing and lowers you in energy. When you break those intermolecular forces, that requires or takes energy. Okay, so when we make those new intermolecular forces, that's stabilizing. That's how we get this lowering in this transition state energy. So energetically, we can think about this as a gain. Right? It is a thermodynamic gain. So some important things as we summarize this slide here to make sure to highlight, we do not see a change in delta G. There is no change in how much. That is, we're going to make the same amount of product, we just get there more quickly. And there's no change in whether. Enzymes cannot take a non-spontaneous reaction and make it spontaneous. Okay? They just make spontaneous reactions faster. So let's go ahead and summarize that here. Okay, so there is no change to delta G. Okay, so the only change for enzymes is that they make delta G double dagger smaller, and they do so by stabilizing the transition state. Okay, so there's no change to delta G. So importantly, that means there is no change in the how much piece. No change in how much. Okay, so we make the same amount of product. And there's no change in whether. We cannot take a non-spontaneous reaction and make it spontaneous. So there's no change in whether. Okay, we cannot take, I'm running out of space here. We cannot take a non-spontaneous reaction and make it spontaneous. Said another way, we cannot take an uphill reaction and make it go downhill. Okay, so all that enzymes really do is enzymes make spontaneous reactions faster. They make spontaneous reactions that will make a set amount of products happen faster. So enzymes make spontaneous reactions faster. All right, so that's how we understand how enzymes work using reaction coordinates.